A really great story in math about really complicated equations starting with the quadratic formula. And ultimately, it's actually related to symmetries of the soccer ball. Yes, the real soccer ball. So in school, we learn the quadratic formula, and this is actually really old. Like this was known in ancient Mesopotamia. This probably isn't exactly the quadratic formula, but it's kind of a cool picture. And it shows if you want to solve this equation, which has degree 2, then there's a way to do it. And you have to take a square root and there are fractions, but it's not too bad. Now, much later than Mesopotamia, in the 15 or 1600s, people were trying to solve equations like this, where it's either a cubic of degree 3 or a quartic of degree 4. And these are two kind of famous people. I think this is Cardano and this is Tartaglia. And they were actually able to do it. They wrote down formulas for solving the general cubic and solving the general quartic equation. These are kind of like parts of or simplifications of those formulas, but you can see they're a lot more complicated. And so what happens next, right? After degree 3 and degree 4, it must be degree 5. What does the formula look like in that case? And the answer is that there actually isn't one. There are quintic equations, degree 5 equations, for which there's no way to solve it, at least using things like radical symbols, fractions, addition, subtraction, things like that. And the way to do that is to use a type of math which is called Galois theory, which tries to relate algebraic properties to what I would call geometric symmetries. And I'm going to explain what I mean by that. So a quadratic equation in general can have two different roots. And if you think about how those roots, what sorts of symmetries they have, it turns out that the algebraic symmetries are basically like that of a magnet, right? You can flip it one end, but that's basically it. Now, a cubic equation, there are going to be 3 roots, and actually those can be interchanged in pretty complicated ways, and it turns out that the abstract algebraic symmetry group is similar to the symmetries of a triangle, of which there are 6, like rotations and reflections included. Now, as things get more complicated, like when we get to degree 4 equations, the symmetry groups are getting bigger. In this case, it's possible that you could have the symmetry group of rotations of a cube. And in general, for a quintic equation, it's possible that you could get the symmetry group of a soccer ball. And that's what this sort of analysis is. Whenever you have a symmetry group, you can try to analyze what are the kind of smaller symmetries inside of it. And you can ask whether those smaller symmetries can kind of be built up to get all of the symmetries. In math, we actually say the group is solvable when that happens. And basically what it means is that we can kind of build a group just a little bit at a time. Beautifully, the relationship of solving those groups or kind of adding things one at a time is exactly the same as in algebra land is adding square roots or cube roots, as you see in this formula here. And so if you want to see how to get a formula like this, well, we had to add in a square root and then later a cube root. And that might correspond to, I don't know, adding a reflection and then adding a rotation. This is all very vague because it's TikTok, but the point is that the symmetry group of the soccer ball is so complicated that there's no way that you could build it up in this way. And so there would be no way to write down a formula that would solve that general quintic equation. And that's what soccer balls have to do with all these formulas.